All right, good morning, everybody. So, a couple of things that I want to talk about real quick before we get into today's material. I forgot to tell you all last time on the notes. I sent the thing through Canvas. I just want to make sure we're all clear on that. Your handwritten notes are fair game on the exam. You can have them. Okay, I get to keep my notebook. I get to use my notes. In the real world, you get to use your notes. Having said that, you can't copy verbatim the book. Okay, these are your handwritten notes that you do. Now, some of you may take notes on a computer or whatever, that's fine, but they have to be on paper when you come in with them, so you have to print them out. So if you do something on a tablet or you do something on a computer, that's perfectly fine. Just print them out and bring them in, because you can't have any devices that have internet access, okay? So, better the notes you take, better off you are. So, it's there for you. You can have all of your personal handwritten notes. Last time, we didn't quite get to the last slide where we were talking about equilibria. What does the word equilibrium mean to you all? Equal, okay, yeah, it's in the name, right? What else might it mean?
Equal on both sides.
Equal on both sides, okay. Balanced, right? So you can imagine a seesaw, right? And you can place equal weights at equal distances from that fulcrum, and that would be in a state of balance. What would happen if you came up and you placed a smaller weight on one side over the other? What would happen to that balance? It would shift, right? It would start going to the other way. In chemistry, when we talk about equilibrium, it's that kind of concept. We're talking about something that when we look at that system, it doesn't look like any changes are undergoing. It's reached a state of equilibrium, a state of balance, if you will. Okay, so imagine that we have a simple reaction where we're going to react A plus B together. Okay? And they're going to give product C plus D. Okay? Simple kind of thing. Right, very generic. When you start off and you mix A and B together, is it in equilibrium? What do we have at time zero, at the moment we mix those things together?
Imbalance.
Just reactants, right? We've just mixed them together and it hadn't had time for a reaction to start yet, right? So we're not at equilibrium yet. Now, you go back into the lab, let's say in 10 minutes, and you look at it, what are you going to start to see? You're going to start to see a change. And what is that change?
The reaction.
Okay, tell me, yeah, you're right, but what are we going to start to see? What are we going to start to see up here? We're going to start to see the products. We're going to start to see C and D, right? What does that mean is happening to A and B?
It's converting.
It's converting, so are we seeing more of it or less of it? We're going to see less of it, right? So over time, right, early on anyway, we'd expect to see the concentration of these things decrease and the concentrations of these things what? Increase. And maybe you come back 20 minutes later and you notice again that the concentrations of these things have decreased and the concentrations of these things has increased. Okay? Then you come back the next day and you notice, wait a second, it hasn't changed from the last time I read it. A and B and C and D are the same as they were last night before I went home. What can we assume about the system?
It's in balance.
It's in balance. It's reached equilibrium. And so what that means is that when A and B come together to make C and D, right, C and D can also do the reverse reaction. They can fall apart to form A and B. And so these are what we call reversible reactions. And in theory, all reactions are reversible. Okay? All reactions are technically reversible. If you know the forward reaction, you by definition know the reverse reaction. It's just going in the opposite direction. Well, what we're trying to describe right now using words is very difficult, right? You can't really communicate that very well with people. You can't say, hey, come in 20 minutes and take a look, wait another day and come back and take a look. So we have to have a way to express this. And the way that we express it, that we chemists express it, is through a constant K called KEQ. It's It's called the equilibrium constant. And it is nothing more than the product of the products. Product means to multiply. Okay, so I take the concentration of C, I take the concentration of D, I multiply those together. And I divide that by the concentration, or the product of the concentrations of the starting materials. Now I've simplified this. We'll learn that this is a little more complicated in chapter 2, but let's just go on with it for now. So KEQ, I can say, hey, this has an equilibrium constant of 10,000. What does that mean? What would it mean if the equilibrium constant is greater than 1? If KEQ is greater than 1, what does that mean for the reaction?
Is product favored?
That's right. We have more products than reactants. What if the equilibrium constant is much less than 1? Then we have more reactants. It's not favoring the formation of the products, right? What if KEQ is huge? Let's say 1,000,000. Really much, much greater than 1. What does that mean? If it was 1,000,000, what would that mean?
Just over more product.
It means I have all products and how much reactants? Very, very, very little, right? And so when your KEQ is 1,000 or greater, we typically take that to mean that the reaction goes to completion. In other words, all of A and all of B will react to give C and D. It's not technically true. There's always going to be a little A and B around, and you can detect them. But for all practical purposes, it's gone to completion. Okay? If KEQ is less than 1,000th, 1 over 1,000, we say that the reaction doesn't go at all. Okay? So there are magnitudes to this idea of equilibrium. Okay? This is going to be a very important concept when we start talking about reaction mechanisms. Okay? Very important concept. What would happen if this had reached equilibrium and you just felt kind of curious and you came in and you just threw in a little D into the mix? The system's in equilibrium and I go in and I just toss in a little more D. And is it going to be in balance?
Yes.
No, it will not be in balance anymore. What will happen? D increases, right? And it's going to try to maintain balance. So that means D is going to react with C to go back and make more A and B to where it can reach balance. Okay? It's a principle called Le Chatelier's principle. We'll talk more about that as time goes on as well. But Le Chatelier's principle allows us to determine and play with the equilibrium to do what we want. Okay? We're going to find out that there are reactions that are in equilibrium, but you can pull reactants out or products out, or you can add more reactants, and you can drive the equilibrium to the side that you want it. Okay? So we'll learn about that in this class as well. So that was the slide that we didn't have time to get to on, when was it, Thursday? And so this will be a concept that will come back many, many times throughout the entire semester. All right, so today we're going to cover chapter 1. We're going to talk about covalent bonding. We're going to talk about shapes. We won't do much with model kits, but I might throw up a model here and there to show you a few things, because your model kits really are all about shapes, right? So we're going to talk about atomic structure, because atoms have a structure that ends up leading to molecules having structures. We're going to talk about a little bit about where the electrons actually are. We're going to talk about how atoms bond together, Lewis structures. Talk a little bit about orbitals, covalent bonding, and then function groups. So we got a lot of stuff to cover today. So let's just go ahead and get right to it. All right, so let's just do a summary of modern atomic theory. You should have learned most of this in Chemistry 106, right? Atoms have protons, neutrons, and electrons. We talked a little bit about this last time. And the important thing to chemists is which one of those? the electrons, right? Electrons form bonds, atoms form bonds with one another, either ionic or covalent bonds, and that results in molecules and compounds and things that we all like to take advantage of, right? So we're going to really focus on the electrons, right? And so what you'll notice when you look at these fundamental particles, right? A proton is the positively charged thing. You already know that. It does have a mass. It's pretty small, right? It's 1.6 times 10 to the negative 27th kilograms, which is tiny, right? A neutron also, it has no charge. It's about the same size as a proton. Notice it's essentially the same mass, but is it an identical mass? No. But if you take the mass of an electron and you take the mass of a proton and you add them together, they get really close to the mass of a neutron. A neutron is a proton that has captured an electron at some point in time. Okay? It's neutral. So if I have a positively charged proton and a negatively charged electron, put them together, they're going to have no charge, right? And then, of course, the electron, of course, we know that that has the negative charge, and we know that it has a very tiny mass. And for the purposes of chemistry and chemists, 10 to the negative 31st kilograms is so tiny that we say it's zero. It's essentially zero. It's not really zero, but it's close enough, right? If I had 10 to the negative 31st dollars, I'm pretty much so broke. I got no money, right? I mean, and so that's what's going on with these fundamental particles, okay? Now, you all know that the nucleus, right, which is where almost all the mass is, right, is in the nucleus. That is where we have the protons and the neutrons. And protons and neutrons will be together in that core of that nucleus. And electrons are going to be in orbitals around it. And we'll talk more about those in just a moment. You might wonder, what is the purpose of the neutron? My physics friends would yell at me for saying it this way. And that's fine, they can yell. But the way that I think about it is neutrons are there to buffer the protons. Do positive charges like to be next to positive charges? No, we know that like charges repel, right? So we're going to take all of these positive charges and we're going to squish them down in this little tiny space. That doesn't seem very favorable, does it? So what nature has decided to do is put a few neutrons in the way, okay, to where the positive charges don't have to get so terribly close. Okay, that's hard to imagine. We're talking about infinitesimally small spaces. But that's how I like to think about it. And it works from the chemist's point of view. Again, physicists would yell and scream, and they have a right to. But from a chemistry point of view, that's good enough. Okay? Because all we really care about is the electrons. Right? Electrons are responsible for making bonds, not protons and neutrons. And I can take A and B and react them together. Their electrons will interact with one another to form new products. Okay? And so you'll have one or more negatively charged electrons, right, that are going to be located in the orbitals around the nucleus. And this is certainly not to scale. I mean, if this was the size of the nucleus, these electrons would be like on Jupiter, right? I mean, it's that kind of scale. It's huge. So small, it's huge to think about it that way, right? And we know that the number of electrons is equal to the number of protons for every atom that is on the periodic table when we look on the periodic table. So if I know that an atom has 6 protons, I know that it has to have how many electrons? 6. I know that if an atom has 11 protons, it must have 11 electrons. But do I necessarily know how many neutrons it has? Not from that, right? How would I get the neutrons?
Check the properties.
Pardon?
Check the properties.
I could check the properties. That's getting more into nuclear chemistry kind of things, and we're not going to focus on that here, right? But I know that these atoms have mass. I know that the protons and the neutrons give all the mass, right? So I look at the mass number. If the atom weighs 13 and it's got 6 protons, I know that it has to have how many neutrons? 7, right? So we can figure these things out pretty easily just using simple arithmetic, okay? So that's all you need to know about the nucleus. It's got protons, it's got neutrons. and that's about it, right? And you've got electrons that go around. And the electrons, the previous model I showed you had them like orbiting like the Earth or the Moon or something, right? That's not what happens. These things are not orbiting like our satellites orbit the Earth, okay? It just isn't that way. They reside in orbitals, which are rooms. Remember last time we talked about my atomic model, or my atomic hotel model for orbitals. And what it turns out for us, fortunately, is that in organic chemistry, you've really only got to worry, for the most part, about two types of orbitals. You have to worry about the s orbital. How do I know it's an s orbital? Because it's spherical. That's easy to remember, right? Sphere starts with s, so it's a spherical orbital. How many electrons can I put in that one orbital? I can put two, right? Each room can only hold two. So this is the type of hotel where the maximum occupancy per room is 2. You can't cram extra friends in, okay? But we also have these p orbitals, okay? And we've got 3 of them, okay? They look like dumbbells, okay? We call them px, py, and pz. Right, so we will call them px, py, pz. What does x, y, and z mean?
Negative 1, 0, and 1.
Pardon?
Negative 1, 0, and 1.
Those are the values that they can have.
Is that the planes they're on?
That's the planes they are in their Cartesian coordinate system, right? So, math, okay. It doesn't get much more complicated than that. But if we think about three-dimensional space, right, we have x, we have y, and we have z, right? And we can define things along those planes. So this is a p orbital that's lying on the x-axis. This is a p orbital that is lying on the y-axis. This is a p orbital that is lying on the z-axis. Okay, so one's this way, and one's coming in and out of the plane of the board. Okay, notice they have different colors. What do those different colors tell us?
There's 2 of them.
Actually, that's one orbital. Blue and red is one orbital, right? So this is a p orbital. There's the dot, right? And we'll just, since I don't have another color, we'll shade one and we'll leave one open. That is one orbital, okay? These are mathematical signs to the solution to the Schrodinger equation. You don't need to know anything more than what I just told you, okay? It's a complicated mathematical equation. But these are signs, okay? And it comes out of a wave equation. And what happens is that like signs will like to bond with one another. Dissimilar signs will not. They will, so it's constructive interference, destructive interference, okay? And so each one of these orbitals has that. Where we have this little dot, you'll notice that it's not colored. This is called a node. Okay? The electrons in this orbital can either be here or here, but they can never be there. Isn't that odd? They can be at the top or the bottom, but they can never be in between. So how do they get there? It's a question I'm not going to have you actually have to answer, right? But it is curious, isn't it? Right? What do we notice about the s orbital?
Nodes are in the center?
Yeah, the electron can be right in the center. It does not have a node. It can exist anywhere in that sphere. Okay? And that's going to be important when we talk about acids and bases. Okay?
Can you say that one more time?
The s orbital, at least the one s orbital, has no nodes. So the electron can actually be right in the center of that orbital. It can't be there in the p orbitals, okay? But it can be there in the s orbital, okay? So we're going to be talking about, in organic chemistry, we're going to be talking about 4 different rooms to put electrons 99% of the time, okay? Couple of important points. The Pauli exclusion principle. You can have no more than 2 electrons having identical quantum numbers. What does that mean? It means that you can put no more than 2 electrons in a room. Okay? That's ultimately what that quantum number nonsense means. Okay? So each atomic orbital can have at most 2 electrons. We also have the Aufbau principle, which states that you are going to fill your atomic orbitals from the lowest energy to the highest energy. That makes sense, right? You're going to do the easiest stuff first and then do the hard stuff later. We all do that, right? Orbitals and electrons are the same way. They're going to fill the lowest energy orbitals first. It's just like in the hotel we looked at the other day. The electrons would go into the first floor before they go into the second floor. Okay? That's what that means. And then we can have what are known as degenerate orbitals. That's px, py, and pz. What do I mean by degenerate? It's not a bad thing. Okay? They have the same energy. They're just pointed differently in space. So an electron can go here just as easily as it can go there or there. Okay? They're the same energy, but pointing differently in space. And then Hund's rule. Okay? You're going to spin pair things. Electrons have to be spinning in different directions to be in the same room. They can't be spinning in the same direction. We'll talk a little bit more about that later. All right. So let's take an example. There's a periodic table. There's carbon. It has an atomic number of 6. So how many electrons does it have? It's got 6 electrons, right? If it's atomic number 6, that means it's got 6 protons. It has to have 6 electrons. Okay, so I've got to find rooms to put those 6 electrons. Also notice that carbon is on the second period of the periodic table. Okay? That's what these numbers are. So 1s means the orbital for period 1, and period 1 only has an s orbital. Why does it only have an s orbital? Because you've only got 2 slots, right? It only needs to accommodate 2 electrons. However, the second period, here, you'll have a 2s orbital and you'll have 3 2p orbitals. Okay? px, py, and pz. So where am I going to put my electrons? Where am I going to start? I'm going to put some in the 1s. How many am I going to put in 1s?
2.
I'm going to put 2 in there. And how am I going to put them in there?
One opposite direction.
Yeah, 1 up, 1 down. Whoop. I guess I didn't. So let's do that. Right, so there's the 1s. So I'm going to put 1 going up, 1 going down. Now where do I go? I go to the 2s. Right? And the 2s and the 2p's are a little different energy. So px, py, pz. Right? So we got to take into account 6 electrons. We just did 2, so we got 4 left. What do I do now?
Fill your 2 box.
Okay. I'm going to put 1 in the 2s, spinning up. Right? I'm not going to go to the p's yet because this is still lower in energy, right? So I'm going to put 1 there. Now how many do I have to take care of? I got to take care of 2 more. So I'm going to go px, py. Notice they are spinning in the same direction. You always put them in the same direction until you start to go back and fill them, and then you put the other ones in backwards. Okay? So these 2 electrons are going to be in their own room. They got lucky on the draw, right? They didn't have to share a room with anybody. That's how carbon is as it sits on the periodic table. But that is not how carbon really works when it makes molecules. It makes what are known as hybrid orbitals. And we'll talk about those as well. Okay? So that's carbon. Take a moment, work with your partner, and work out oxygen. All can get together, it's fine. Just take 2 minutes. Let's work out the atomic structure for oxygen. From an electron point of view, what's the difference between carbon and oxygen?
More electrons?
2 more electrons, right? That's it. Right? So now, what do I need to do to this to get oxygen?
Or one of the PZ.
I'll add 1 to the PZ, and then I'll do what? That's right. That's what oxygen looks like on the periodic table. Okay? Electronically. Okay? Good. We also have to be concerned about core electrons and valence electrons. Okay, I'm going to put this back to carbon because I like carbon better than oxygen. Although I'm breathing a lot of it right now. Right? What is a core electron? What are core electrons?
An electron with the previous or the first or the previous valence shell.
Okay, that's close. Yep. So if I was looking at carbon, where are the core electrons? Those are the core electrons. Those electrons do not do any chemistry for all practical purposes. Why?
It's just 1s2 or 1s or it's just.
It's the electrons in the everything below the valence shell, which is the upper energy shell, right? So these aren't going to do any chemistry. They're too low in energy. This is the highest set, right? It's the 2. So all of those electrons are in what we call the core, or the valence shell, okay? So your core electrons are below the outermost shell. So this is, should have put a 2 up here. Right. So 2 is my outermost shell. So all of the electrons in that outermost shell are called valence electrons, okay? So how many valence electrons do I have? 2? Valence? I got 2 core. How many valence do I have?
4.
I've got 4. All the electrons in that outer shell, the 2 shell, are my valence electrons. That means carbon has 4 electrons that can actually do chemistry. Okay? How many bonds can carbon typically form? Do anybody know that from Gen Chem?
4.
It can form 4, right? Which kind of makes sense since it has 4 valence electrons, right? But if you look at it a little further, you might go, well, maybe it could form 2 because it's got 2 unpaired and it might want to react, okay? So there's some other business that can actually go on, okay? And so we need to distinguish between the core and the valence, okay? The core electrons, from my point of view, all they are there for is to balance the charge of neutrons. That's all they do. The valence electrons also balance charge with neutrons, but they also do chemistry. They react with other electrons and they make bonds and they do things, okay? And since these are in the highest energy shell, they are the most readily available. If another carbon atom comes in and bumps into this atom, it's going to be that outermost energy or outermost shell that's going to touch each other, right? And then our core is not going to do anything, okay? So that's how chemistry can occur, okay? So, how do we determine the number of valence electrons that a atom has? Do we have to go through and do all this? You can use the group number. That's the beauty of the periodic table. The way that things get arranged, when you start to arrange the periodic table based on atomic number, it's amazing what kind of trends start to form. They're trends. They're not identical things, but there are some things that are identical. So, for example, when I look at the periodic table and I see carbon sits in group 4, that means it has 4 valence electrons. How many does silicon have? 4. How many does germanium have? 4. Right? They've all got 4 valence electrons. They're not the same 4 valence electrons. Silicon's 4 valence electrons are higher in energy than carbon's, and they can do different types of chemistry, but nonetheless it has 4. Okay? So that's the beauty of the periodic table. I will supply you with a periodic table on each and every exam. I do not expect you to memorize the periodic table, but I do expect you to be able to use the periodic table as you were taught in 106 to know some general trends, right? So how many valence electrons does hydrogen have? 1. How many valence electrons does nitrogen have? 5. That's right. So we can get all of this stuff simply by looking at the periodic table. Okay, so there's a lot of power, you know, what was it, 2 years ago was the year of the periodic table? The 150th anniversary of Mendeleev actually putting it all together, or Mendeleev, excuse me, putting it all together. Beautiful thing, right? And there were many trials and putting it all together, and people were like, well, if you put it together like this, it just doesn't seem to work. He came together and he said, well, you know, if you start doing this stuff by atomic number and doing this, very powerful thing. And he was actually able to predict, because there were holes, there must be elements that exist in nature that we haven't found yet. And in fact, we found them, okay? Because of the way that this all falls together, okay? It just took us millennia to figure it out, okay? Yeah?
What's the deal with the core electrons for hydrogen and helium?
Well, it's interesting. So the core electrons and the valence electrons are the same thing in those, aren't they? Yep. So the core electron for hydrogen, it only has one electron. It is a core and a valence electron, so to speak, right? Really, I just think of it as a valence electron because the cores don't exist. Okay. Or there's nothing below one, right? So chemical bonding, right? So there are two types of bonds that we're going to talk about. But in all cases, really what a bond is a force that holds atoms together in a compound. That force can either result from the sharing of electrons in forming what we call a covalent bond, or that force can come from opposite charges attracting each other, which comes from what we call ionic bonding, okay? But all bonding occurs from the valence shell electrons. Core electrons do not do anything for bonding. And you're going to need to know how to do Lewis structures. Did you all do Lewis structures in Chem 106? Okay. Doesn't change here. The only difference is I'm not going to tell you, give me the Lewis dot structure for SF6. It's going to be carbon, hydrogen, nitrogen, oxygen, pretty simple things. And we're going to learn shorthand, right? You're not going to have to build a huge organic molecule and draw out all of the symbols and put all of the dots all of the time. Organic chemists are lazy by definition, and we like to have shortcuts because our molecules are so big. If you had to put dots around a biomolecule, oh my God, you'd be there all day just drawing dots, right? So we had to come up with some shorthands, and those shorthands we'll teach you about as well. Okay? So, here's some examples. You all have probably seen these in Gen Chem. So here's boron. Where does boron sit on the periodic table? Let's look real quick. What group? 3. So it should have how many valence electrons? 3. Right? And so what we see is, in fact, it has 3. It's got one s2. Those 1s electrons are the core electrons. Right? Those are these. And it's got 2 in the 2s orbital and 1 in the 2p orbital. These in the red box are what electrons are these? These are the valence electrons, right? This is the Lewis dot structure that you learned about. You draw a B and you put dots, right? These two are paired together. This one is all by itself. So this electron I know has to be the 2p in the 2px orbital, okay? We can also look at phosphorus. Okay? It has valence, it's in the third row, so it's 3s2, 3p3. So this is all what is called the neon core. That's what neon looks like, so we're just going to ignore that. That's the core electron. And it's got 2 in the 3s, and then 3, 1 apiece in the 3p's. And you can see how we did that in the dot, right? You got your paired electrons, and then each of your single dots. Okay? So how many bonds might you think phosphorus can form? Theoretically, it could form up to 5 bonds, and we do see examples of that. But you might look at it and go, well, it's got 3 lone electrons that aren't paired with anything. Maybe it'll form 3. There are examples of that. Okay, so there are many examples of phosphorus doing a lot of different types of bonding, but it all comes from the fact that it has this general Lewis dot structure. Okay? The good thing about organic chemistry is 99% of it is covalent bonding. So we're going to be dealing largely with covalent bonds. Okay? And so they will form these chemical bonds by sharing electrons. Why do you suppose organic molecules or carbon likes to form covalent bonds as opposed to ionic bonds? Why would 2 carbon atoms come together and want to share electrons as opposed to form an ionic bond? Here's a general rule of thumb. The further apart in the periodic table your atoms are, the more likely they are to form ionic bonds. That's why it's things like sodium and chlorine will form sodium chloride. They're far apart on the periodic table. Sodium would rather give up its electron to chlorine and form an ionic bond. But where is carbon and carbon on the periodic table? They're the identical spot. One carbon is not any more hungry for an electron than the other one. So instead of trying to win a tug of war, they just reach an agreement and decide to share it. Okay? So now, where is oxygen on the periodic table? You're close. Yeah, so here's carbon, here's nitrogen, here's oxygen, right? It's fairly close to carbon, so it will also like to form covalent bonds, right? And so a lot of the things that bond with carbon are very close to where it sits on the periodic table, and so you get covalent bonding, okay? Here's the simple example that you should have learned in Gen Chem about 2 hydrogen atoms coming together to form a bond, right? Hydrogen does not exist as it does on the periodic table. You can't go out in nature and find H dot. Doesn't exist. When we look out in the cosmos, we do all the stuff, we see H2. And that's because 2 hydrogens come together and share their electrons to form a bond. Okay? So you've got one hydrogen that has an s electron, you've got another hydrogen that's got an s electron, and they form a bond. I've got 2 orbitals coming together to form a bond, but orbitals are conserved. I can't create nor destroy orbitals. So if I'm going to bring 2 orbitals together from the atoms, and I'm going to create a molecule, hydrogen is a molecule, I have to create 2 molecular orbitals. You probably learned a little bit about molecular orbitals in 106. The good thing is that organic chemistry only deals with a few elements, so it's a pretty simple thing, right? So I have 2 atomic orbitals coming together to make 2 molecular orbitals, and the electrons are in the lower energy molecular orbital that we call a sigma bond. We'll talk more about that later. What's this orbital? Why does it have a star? It's not a pi bond, but we will talk about pi bonds. What would happen if I start to put electrons in that orbital? Would hydrogen still exist? No. Is that pi star orbital, or that sigma star, excuse me, made me say pi. That sigma star orbital, is it higher in energy or lower in energy than everything else? Is it lower? It's up here, right? It's higher, right? This is called an anti-bonding orbital. Anti-bonding, yeah. So as we start to put electrons in here, this bond gets weaker and it'll eventually break, right? What's the difference between hydrogen and helium? A proton and an electron, right? So if this was helium, this would have 2 electrons, right? If this was helium, it would have 2 electrons. It would still form the same molecular orbital diagram. I'd have 2 electrons here, but what would I have to do with the other 2 electrons? I'd have to put them up here. And if that happens, what happens to the bond? It completely breaks. This is why dihelium doesn't exist. You will not find dihelium in the universe. Okay? It just doesn't exist. Okay? All right. We need to know a little something about electronegativity. Just because two things are sharing electrons doesn't mean they're sharing them equally. Just like when you share a hotel room with somebody, you're not necessarily sharing that room equally. Some of you spread out, some of you take more than your fair share of the drawer space, some of you hog the counter space in the bathroom, right? And that's okay. That's just the way it works sometimes. And the same thing happens in bonds, okay? And so when we have two atoms that are sharing electrons, if one of those atoms is more electronegative than the other, those electrons, even though they're shared, are not going to be shared equally. And those electrons are going to be more closely associated with the more electronegative atom. So what do we know about electronegativity in the periodic table? We know that fluorine is the most what? Is electronegative. And we know that cesium and francium are the least electronegative. And we know that the trend goes from here to here, right? So if I'm making a bond, a covalent bond between carbon and fluorine, they can share electrons, but who's going to win? Fluorine's going to win, and it's going to have what we call a dipole. The electrons are going to be closer to fluorine than carbon. Even though they're being shared, they're not being shared equally. Okay? That's common. Okay? So let's look at some examples. Here's an example. This is a model of two fluorine atoms bound together. This is how fluorine exists in nature. Is this a polar bond? Nope. Why is it not polar?
Symmetrical.
It is symmetrical. Fluorine is the most electronegative atom, but so is fluorine. And when they're sharing, they're pulling on each other with equal force. It's not a real force, but with equal force. And so you will find that the electrons are equally distributed across that bond. These shades in your book, they explain to you what these shades mean. These are molecular orbital calculations that come out of a computer, okay? The redder areas tell you where the electron density is. The bluer areas tell you where electrons are absent, okay? So, that's fluorine. Let's look at hydrogen fluoride, HF. Hydrogen's over here on the periodic table, fluorine's over here, far or close? Far, right? Which one's more electronegative? Fluorine. So fluorine is going to pull the electrons to itself. Notice how the fluorine has all this red. Notice how the hydrogen has this bluish area. It is a polar covalent bond. They are sharing, but fluorine's winning in that sharing. It's getting the 60-75%, right? Right? So, it's in a relationship, but they ain't sharing the chores equally, okay? Fluorine's getting its more than its fair share of the electrons because it's more electronegative, okay? So here's some examples of polar molecules. What is that? That's, sorry about that. That's HCl, okay? So you can see the hydrogen and the chlorine. Chlorine being more electronegative is pulling electrons to itself. Notice how we draw a dipole, plus and the arrow. The arrow tells us the direction of the electronegativity, right? The plus sign tells us what side of the molecule is positively charged, right? So that has a dipole going in that direction. This is water. Notice that the dipole on water isn't from the hydrogens, it's from between the two hydrogens, right? So it has to be symmetrical, right? But oxygen is clearly more electronegative than hydrogen, so it's pulling those electrons to itself. This whole idea of water being polar is why water is liquid on Earth. By its weight, by its mass, water should be a gas on Earth. But because it's polar, it can do some funky stuff that we'll talk about, and it allows it to be liquid. And it allows it to be liquid actually up to 100 degrees Celsius. Okay? And then this is an organic molecule called acetone. Don't worry about the name. carbon with 3 hydrogens attached to it, bound to a carbon that's doubly bound to an oxygen and bound to another CH3. It is a polar organic molecule.
Yeah, I think earlier in the lecture you had mentioned sulfur hexafluoride or
SF6?
yeah, SF6. Is that also polar? No?
Because it's symmetrical. Yeah, it has polar bonds, but it is overall nonpolar. So we'll talk about some examples of that in just a moment. Folks, this is your fingernail polish remover. Acetone. It's organic. It will dissolve the organic stuff that is your fingernail polish, but it'll also rinse off in water. Why can't it do both? Because it's polar, slightly polar. Okay? And it can dissolve the paint and the pigment, and it can wash it off in the water. But you put your fingernails in the water, your paint just doesn't come off, right? You got to have this molecule that can interact with water and with organic stuff, and it turns out acetone does a pretty good job of that. Here's an example of a molecule that has polar bonds that isn't polar. Carbon dioxide, right? I think you all will agree that carbon and oxygen have different electronegativities. Oxygen being closer to fluorine is more electronegative than carbon. It's pulling electrons to itself. So this is a polar bond. But I also have a polar bond in exactly the opposite direction that cancels that one out. Shape matters. Shape matters. So all molecules, you have to look at the shape. Yes?
Wouldn't the shape be linear though?
It is linear. That's right.
So why?
When I look at it from this way, I see the same thing as if I look at it that way. I see exactly the same thing.
So why would it not be nonpolar?
It is nonpolar. It's got polar bonds, but it's a nonpolar molecule.
Oh.
Okay? So, all polar molecules must have polar bonds, but not all polar bonds lead to polar molecules. Okay? Very important. Okay? Quick review on drawing Lewis structures. These are kind of some rules to live by, okay? The first thing you're going to have to do is find the total number of valence electrons supplied by all of the atoms in the structure. So if I give you a molecule and I say do the Lewis dot structure, the very first thing you're going to have to do is figure out how many valence electrons you got total that you got to take care of. Then you're going to write down the skeletal arrangement of the atoms, how they're connected with one another, okay? And usually you get that through experiment, so that means I'll give it to you on the exam. I'll tell you how things are connected. But usually, you learned in Gen Chem that the least electronegative atom is usually the central atom. Usually that's carbon, okay? And then you need to remember some normal bonding things. It'll make life a lot easier for you. Hydrogen forms one covalent bond. It doesn't form two, it doesn't form three, okay? Halogens, chlorine, fluorine, bromine, iodine, they typically form one covalent bond in organic chemistry. Oxygen typically likes to form two covalent bonds. Nitrogen likes to form 3 covalent bonds, and carbon likes to form 4 covalent bonds. These are rules to live by from an organic chemistry perspective. Are there examples where carbon has less than 4 covalent bonds? Yes. Are they common? No. Okay, so we're talking about things that are common. Can hydrogen actually form more than one bond? Yes, it's called hydrogen bonding. Okay, it can happen. But for the most part, we consider it to only take on one covalent bond. All right, so let's look at an example here, and let's draw the Lewis structure together for this molecule called phosgene. Okay? The name phosgene always confused me because it sounds like it ought to have phosphorus in it, but it doesn't. It was a chemical that was utilized in World War I as a chemical weapon, but it's also a very useful molecule. It has a carbon that's connected to an oxygen and two chlorines. Okay, that's the connection. How many electrons are in each one of these sticks? 2. So I've used 6 electrons already. Just putting together the thing. I know that carbon comes in with 4 valence electrons. I know that oxygen comes in with 6 valence electrons. I know that chlorine has 7 valence electrons, but I've got 2 of them, so that's a total of 14. So when I add all that together, I've got 24 valence electrons that I have to account for. I just took care of 6. How many do I have remaining? So I got 18 valence electrons that I gotta take care of. Where do I start putting them? Could start with chlorine. Why would I start there? I'm not disagreeing with you.
Oh, that's just where I would start.
But why? Why would you start there? It's a good.
Well, it doesn't really matter where you start unless there's hydrogen in the molecule.
Okay. But I usually start with the most electronegative atom. Chlorine and oxygen are pretty close, but chlorine's good enough. Right? Why would I want to start with a more electronegative atom? Because it wants the electrons, right? So, we're going to put 1, 2, 3, 4, 5, 6. I can't have any more than 8, right? 1, 2, 3, 4, 5, 6. Right, and so that's 12, right? So I've got how many more left? I got 6 electrons left. I'm gonna have to do something, right?
Yeah.
Yeah. How many electrons do I have around carbon?
6.
And how many does it want to have?
8.
It wants to have 8, so what can I do?
Double bond oxygen.
That's right, so I can take these electrons and make it actually a double bond, right? And now I've taken care of all my electrons. I now have my molecule phosgene all written out, right? What is the octet rule? What does it mean? Once 8. I'm going to tell you what my pet peeve is in Gen Chem, is that they teach you in high school and they teach you in general chemistry wrong about the octet rule, okay? The octet rule exists because the second period where carbon sits has a 2s orbital and 3 2p orbitals. Each orbital can have how many electrons? 2. So 2 times 4 is 8. That's where the octet rule comes from. The second period can hold no more than 8 electrons. Does every atom in the world sit in the second period? No. But you learned in high school chemistry, you might have learned in Gen Chem, depending on who your teacher is. Well, when you go down to sulfur and you go down to, it's the expanded octet. There's no such thing as an expanded octet. 8 is 8. If you expand 8, it's called 9, 10, 11, 12, right? You can't expand 8. 8 is 8. The octet rule only holds for the second period of the periodic table. Okay, you probably even learned that oxygen or hydrogen's octet is 2. Well, that doesn't make any sense. 2 is 8. It is not, right? What we're really talking about with the octet rule is that you want to have all of your valence orbitals completely filled. And then they start to look like the noble gases. It's really the noble gas rule. Yeah.
Yeah, during general chemistry, we've also learned that some of them have exceptions to the octet rule, such as boron, that can be stable with 4 electrons.
It can be stable, that's right. So there is stability that can occur, and carbon can do that a little bit too. Not as stable. But again, that depends on where things sit on the periodic table, right? And so there really is no exception to the octet rule. Boron can still take 8 electrons. It can just be stable with fewer because of where it sits on the periodic table. That is true. Okay? But for the most part, we're not going to deal with that. Okay? Now, the thing that you also have to do, and this is a very important concept that you probably didn't do in Gen Chem, maybe you did. At one time they didn't teach it here. Again, another thing that drove me crazy. You also have to determine formal charge. Formal charge is going to give you a lot of information when we start talking about organic reactions. Okay? And so you learned an equation in Gen Chem, maybe, in terms of how you can calculate formal charge. Okay? Throw that away. It's just something you have to remember, and it's useless. The easiest thing to remember is that all you got to be able to do is draw a circle and count. So if I wanted to know the formal charge on the oxygen atom, all I got to do is draw a circle around it. Okay? And then you count the electrons that are inside the circle, and you count and you subtract those from the valence electrons. Formal charge is always the number of valence electrons minus the number of electrons formally owned by the atom. How many valence electrons comes in for? No, oxygen. 8, 4. No, you're right, 6. Yeah, I'm sorry. Yeah, so you got 6, because carbon is in group 4, nitrogen is in group 5, oxygen is in group 6, right? How many does it formally own right now? It owns that pair, they're inside the circle. It owns that pair, they're inside the circle. But the circle's cutting these bonds, so what does that mean? Yeah, it cuts them in half. This is where the formal comes in. Even though this is a polar bond, formally we say when the circle cuts it, one electron goes on the inside, one's on the outside. So how many is that total? 1 here and 1 there, right? So 6 minus equals 0. That has a formal charge of 0. Let's look at this example. What is the formal charge of that oxygen atom? What would I do?
6 minus 5.
I'm going to take the valence electrons, which is 6, and I'm going to subtract from it the formal number that it owns. Yeah, it owns 7, right? So it has a formal charge of -1. We call that methoxide. Don't worry about that yet. But it does have a formal negative charge. Okay? That's the easiest way in the world to calculate formal charge. You take the valence electrons minus the number that are formally owned. And you all learned the valence electrons minus the number of non-bonding electrons minus half the number of, just draw a circle. It's easy, right? Easier to see, easier to do. Okay? Now, in terms of computing formal charges, that takes time. There are some motifs that you just need to know. Carbon with 4 bonds is always going to have a formal charge of 0. It doesn't matter whether they're single bonds, double bonds, triple bonds. Carbon with 4 bonds is going to be 0. Nitrogen with 3 bonds and its lone pair, I need to add that. Doesn't matter what kind of 3 bonds, 3 single bonds, a double bond and a single bond, a triple bond, but any 3 bonds and its lone pair, those are going to be 0. Oxygen that has 2 bonds, it could be a double bond, it could be 2 single bonds, but 2 bonds and its lone pairs of electrons, it's going to be 0. And then the halogens that all have a single bond, those are all going to be 0 formal charge. Okay? So, if I was to show you acetone again, what's the formal charge on oxygen? 0. It's got 2 bonds, right? I just didn't draw on the lone pairs. What's the formal charge on carbon? 0. It's got 4 bonds. What's the formal charge on that carbon? It's got 4 bonds. 0. 0. Okay? You can figure that out really quick by memorizing those bonding patterns for things that have formal charges of 0. How many bonds to carbon gives a charge of 0? 4. How many to nitrogen? How many to oxygen? How many to halogen? What did we just do? 4, 3, 2, 1. Right? You know that from the periodic table. Just carbon is 4, 3, 2, 1. Figure it out. Okay? All you gotta do is count down, so to speak. There are some structures, okay, there are some structures, what did I do with my? Where a single Lewis structure isn't sufficient to explain the bonding. An example is this molecule that's shown here. Let me just draw it out for you. H, C, double bond O, lone pair, nitrogen, has a hydrogen attached to it, and it also has a negative charge on that nitrogen. Why? Because if I circle that, nitrogen comes in with how many? Comes in with 5 and it owns 6. Right? So it's got to have a negative charge on the nitrogen. Okay? If I go do an experiment on this molecule, what I find is that the charge isn't completely on nitrogen. Some of it's on oxygen too. Those electrons don't necessarily completely belong to nitrogen, even though that Lewis structure says nitrogen gets 2 lone pairs. But I can also draw a Lewis structure where I'm accounting for all of the electrons that looks like this. And the negative charge is now on oxygen. These structures are called resonance structures of one another. And we indicate resonance structures by using a double-headed arrow. I want you to be very careful when you look at Lewis structures. It does not mean that half the time it looks like this and half the time it looks like this. These are not in equilibrium with one another. There is only one molecule. What it means is that these electrons do not belong just on that atom. They are delocalized across this system right here. Okay? I know that can be kind of hard to grasp. But the Lewis structures have a fundamental flaw in them when Lewis proposed them. Some Lewis dot structures perfectly account for the shape and structure of a molecule. In this example, it does not. If I was to look at this in a magic microscope, what do we know about single bonds? Are they longer or shorter than double bonds? They're longer, right? So if I was looking in a magic microscope, and we do have these things, by the way, they're not called magic microscopes, but I could look at this, I might expect if this was the real structure that this would be a long bond. Or if it existed only as this, it would look like a short bond. But when I take this and actually put it under the microscope, I see that it ain't this and it ain't that. It's in between. It is shorter than a single bond, but it is longer than a typical double bond. And that's because these electrons are actually delocalized. It also means that this carbon-oxygen bond is not quite a double bond, nor is it quite a single bond. It's somewhere in between. That's what resonance helps us understand. Yes, ma'am?
So why do we have the negative over nitrogen or oxygen in the first place?
Well, if I took care of both of these structures takes care of all of the valence electrons. Okay? Now we have to calculate formal charge. Formal charge for this would be 0, 0, 0, 0, but this would be -1. That's why we put the -1 there. Okay? However, when I look at this one would be 0, 0, 0, 0, but when I calculate this one, it would be -1 there. Okay, so you have to actually calculate the negative charge. I didn't go through that calculation. I knew it because of how things were bonded together. Okay? We will talk an awful lot about resonance structures as we talk about reaction mechanisms. And I will give you what you need when you need it, okay? You're going to, again, we're covering just a little bit of this at a time, okay? All right. It turns out that methane, CH4, is carbon and 4 hydrogens, and it is shaped like a tetrahedron. So there's a carbon that's tetrahedrally shaped, and I'm going to try to find 4 white spheres. And we're going to use these white spheres as examples of hydrogen. So this is carbon, and it forms a bond between a hydrogen, another hydrogen, another hydrogen, and there we go. So this is called methane. This molecule, let's assume these are all the same length. I know, there we go, pretty close. That's what methane looks like. You see that on the picture right there, right? It's called tetrahedral geometry. This geometry cannot be accounted for by the orbital diagram or the atomic orbitals of carbon as it sits on the periodic table. Right? This is the ground state for carbon. I've got 2 electrons in the 2s orbital, and I've got an electron in the 2px and the 2py. Px and py. What's the angle between x and y? 90 degrees. Does any of that look 90 degrees? Not at all. Plus, you might look at that and say, wait a second. Hydrogen has a lone electron, and it wants to react with something that has a lone electron, and carbon only has 2. So maybe methane should just look like that. But it doesn't. It looks like this. And that's because it undergoes what's called hybridization. So the 2s orbital and the 2p orbitals get together, and almost magically, through energy is involved, it's not magic, they rehybridize into what are called hybrid orbitals. And so what happens is an electron from the 2s orbital gets promoted in the energy. And now you've got 4 orbitals that all have a single electron. Well, that can account for the fact that you have 4 bonds to carbon. But still, px, py, and pz, they would be at 90 degrees to one another. These aren't 90 degrees, right? So what's going on? Well, we form, again, like I said, we form hybrid orbitals, okay? And those are called sp3 hybrid orbitals, and we'll talk more about that in just a moment. But that's one example. Let's look at ethene. That's what ethene looks like. You can build a model for it. I don't have time to do it today, right? That's kind of what ethene looks like. It's CH2, double bond, CH2, okay? The bond angles are approximately 120 degrees. It lies in the plane of the board. That's what the little box is showing you, okay? Those are the orbitals that you're seeing, okay? Again, that shape does not come from the atomic orbitals of carbon. It comes from a different hybrid, okay? And so, again, what happens is, right, you get promotion. Where did that happen? Actually, you're supposed to get one of those electrons to populate. I don't know why that didn't populate up. But then these hybridize into what are called sp2 orbitals, okay? So carbon for ethene is called an sp2 hybridized carbon atom. This is an sp3 hybridized carbon atom. So carbon atoms that have all single bonds are sp3 hybridized. Carbons that have one and only one double bond are called sp2 hybridized. What do you think it's called if we have a carbon atom that has a triple bond? This is sp3.
SP2.
sp2 is ethene.
SP4.
sp1. We just call it sp. Okay? And we'll learn about that as well. Okay? So here's the easy way to figure out what your hybridization of your orbitals are. If carbon has no double bonds or triple bonds, no multiple bonds, it's called sp3 hybridized. If it has one multiple bond, okay, it's sp2 hybridized. And if it has 2 multiple bonds, we say that it is sp hybridized. The easy way to remember it is 0, 1, 2, 3, 2, 1. 0, 1, 2, 3, 2, 1. Okay? So, let's look at an example here. What's the hybridization of that carbon? What's the hybridization of that carbon? sp2, because it has a multiple bond, one multiple bond, right? What's the hybridization of that carbon? It's got all single bonds, right? sp3. What is the hybridization of carbon dioxide? sp. Okay? So you're going to learn an awful lot about these different hybridization models as we go on. Okay? So you can put a lot of these different hybridizations together. This is an example of a molecule that contains nothing but carbon and hydrogen, and you'll notice that it has two carbon atoms that are sp hybridized, and it's got two carbon atoms that are sp3 hybridized. Okay? And it works because of the octet rule. Okay?
Does this structure with the 3 up, 3 down only work with carbon? Hybridization only occurs with carbon?
No, it does not. Hybridization can occur for any element on the periodic table, but for our purposes, we're going to be focusing largely on carbon, oxygen, nitrogen. So we'll talk about hybridizations of those atoms. But the big piece for organic chemistry is carbon. Okay? All right, we're coming to the end. We're going to finish up with this one slide on functional groups. One of the things that you all need to do, if there's anything you memorize your functional groups. Okay, we will start next time with going over table 1.9. This is in your book. Okay, you need to commit to memory right now these functional groups. Okay, the hydroxyl group, which we call alcohols, the amino group, which we call amines, the carbonyl group, which can be aldehydes or ketones or carboxylic acids. Notice they are different. Functional groups are a collection of atoms that come together that have a similar function, or have a defined function, excuse me. Okay? If you know the chemistry of your functional groups, you'll be able to do well in this class. You will not, by memorizing these, know the chemistry of these functional groups yet. It's just step one. Okay? I am looking forward to seeing you all on Thursday. We have finished chapter 1 today, which means that Thursday is fair game for a quiz over chapter 1. So make sure you have all of your stuff worked out in your book so that at the end of class, like right now, I'd say turn in problem whatever. You would write your name on it, turn it in, and walk out of the classroom. Have a great rest of your day, and I'll see you all on Thursday.